Hey y'all, so here's an energy balance for a closed system, and I'll talk about why the concept of enthalpy comes into play. What I'm showing is a frictionless piston cylinder arrangement. There's a red brick on it, and it's got some weight, and the weight of the brick and the surface area of the piston manifests itself or creates a pressure within the cylinder itself. So let's say we add a little bit of heat to this device. We're going to put a little burner onto the bottom of it, and we add some heat Q, and that causes the brick to move upward as the gas expands, and consequently we've got boundary work done. The system is doing boundary work. It's lifting the brick, or there's a pressure and an increase in the volume of the brick going up. So the energy coming in, energy coming out, we could say that the energy coming in minus the energy coming out has got to equal the amount of energy stored. So what I'm doing is implicitly I'm doing a control volume. I'll highlight it here. But all of the energy coming into this control volume minus all the energy leaving has to go somewhere. And in this case it's being stored as internal energy of the gas. So in the notation we're used to, we'll say Q is the energy coming into it. Energy leaving is the boundary work that was done. And that'll equal the amount of energy stored, or the increase in internal energy of the gas. And the boundary work is simply the integral of P dV. So we're going to integrate from the initial volume to the final volume. And if the pressure is constant, in this case it's constant because it's dictated by the weight of the brick and the surface area, it's constant. So we'll pull that, the pressure is constant, it comes out of the integral, and we're left with P delta V for the boundary work. So if I make the substitution and rearrange, I've got Q is equal, the amount of heat entering is equal to the change in internal energy plus P delta V. And by definition, we're just calling this letter H enthalpy. We're just saying that's U plus PV. It means delta H is equal to delta U plus PV. And in this case, it's equal to delta U plus delta PV. Or because the pressure is constant, it's equal to delta U plus P delta V. So Q is equal to delta U plus P delta V, which is simply equal to delta H. It doesn't just have to be with heat, so we could make it more general. We could say the sum of all ways energy can get into this control volume. I used heat as one example. We could also have electrical work coming into it. We could say W sub E for electric. Let's say there's electrical work coming into it. There might also be some heat coming into it. There might be some shaft work perhaps coming into it. And so all the energy coming in, the amount of energy that came in minus the amount of boundary work that the system did, was equal to its change in internal energy. So if we had a kilojoule of electrical work, a kilojoule of heat, and a kilojoule of shaft work, we would expect the internal energy to increase the internal energy plus the boundary work, so delta U plus the boundary work. We would expect the sum of these two to increase by 3 kilowatts. So 1 kilowatt of electric, for example, 1 kilowatt of heat, and 1 kilowatt or kilo. What I'm trying to say is that the amount of energy entering the system, if we've got 1 kilojoule of electrical work, 1 kilojoule of heat, plus 1 kilojoule of shaft work that crossed the system boundary, that will equal 3 kilojoules increase in the enthalpy of it. So let's say, for example, we go from state 1 to state 2, and state 1 is saturated water, which means it has a quality of 0. Any amount of heat would cause a little bubble of vapor to appear in the water. So saturated water, quality of 0. And let's say the pressure at state 1, P1, is equal to 200 kilopascal. In state 2, we've got saturated vapor, which means the quality is 1, and P2 is also equal to 200 kilopascal. P2 is equal to P1 simply because we've got the same brick on this frictionless piston. Because I know I've saturated water, I know the quality of it, and I know the pressure, I can look up in the saturated water table the enthalpy at state 1, and I'll find that enthalpy is 504.8 kilojoules per kilogram. I can get the same thing in ease using this command, which will give me the enthalpy of water at a pressure of 200 kilopascal and a quality of 0. So saturated water, quality of 0. And I can do the same thing for state 2. I get H2 is equal to 2,707 kilojoules per kilogram. And here's the analogous command in ease for H2, and in this case I'm using a quality of 1. So if, for example, you wanted to figure out the amount of energy needed to go from state 1 to state 2, in which some boundary work is being done, it's doing so under constant pressure, we could say that the total amount of energy in has to equal delta H. And if we said, for example, there was a mass of 1 kilogram of water, in this case the total amount of energy in has to equal the mass times the change in specific enthalpy. So in this case we'd have 1 kilogram. 1 kilogram times 2,707 H2 minus H1. And the difference in those is equal to 2,200 kilojoules. So a way to rephrase the question is that to get from state 1 to state 2, saturated water, we're going to boil it all into a saturated vapor, saturated liquid to a saturated vapor. Energy in any form needs to cross the system boundary in the amount of 2,200 kilojoules. So 2,200 kilojoules, it could be heat coming in, it could be 2,200 kilojoules of electrical energy coming in. Any form of energy crossing the system boundary would get us from state 1 to